going to start a new category of functions. We've just been looking at polynomial functions. And now we're going to be looking at a category of function called rational functions. And we're going to spend 2 days on this instead of trying to cram it all into one day. So a rational function, we'll be looking at the definition for it in just a minute, but here's a graph of a function, and this function looks a little different than functions that we just got through learning about, the polynomial functions, because polynomial functions were a smooth continuous curve over all real numbers. You could start at any point on the curve and trace it without lifting your pencil off the paper at all. Whereas if we try to trace this one, you notice if I started here and came down and I sort of followed this along, in order to get to this part of the graph, I'd literally have to lift my pencil off and then start over here. So this doesn't have the same features as a polynomial. The other thing is, you notice it has this dotted vertical line here, which we haven't seen before. So let's take a look. That's why I put the little toolkits on there, so later on when you're graphing, you can use some colors, because this dotted line that goes right down through x equals 1 is a new feature. Huh? Whatever I'm drawing? Okay. Okay, there we go. So we've got this dotted line that we haven't seen before. And anybody notice anything else that's kind of weird about this? It doesn't touch these axes, so it has, this particular one has, it doesn't look like it has, oh, I had so much trouble with the pen today. I had to switch pens out. Okay, let's see if it works now. So, all right, a couple of questions going on. Mahendra, did you have a question? Yeah. Yep. That means I'm including 2 also. Thank you. So what's the next part of the domain? It just goes from 1 to 2, right? There we go. That's sharp. Caught that one. 1 to 2 is the next piece of the domain for which this function is defined. And then it would be 2 to infinity, right? Okay. Liam? Well, that's why we're using parentheses, because 2 can't be included. So when we don't include the numbers, that's when we use the parentheses. Okay? It's sometimes easy to get them mixed up. That's what happens. So yeah. So hopefully I can write this without my pen going wild again on me. 1, 2 union with 2, infinity. Jasper, did you have a question about that? Same question. Okay. So, okay. We got the domain, the 2 excluded values. You see the excluded values are 1 and 2. So that's going to break up. If you think about it, just think about an x-axis and sort of having 2 points, 1 and 2, where your function's not defined. That's going to set it up into 3 different sets, from negative infinity to 1, 1 to 2, and then 2 to positive infinity. But as you can see, this is the one-time set notation is actually much more efficient. I don't care for a quiz or a test how you answer. You could do these intervals with the union sign, or you could do the set notation. It's just for those of you doing homework. I wanted to show you the interval. Vertical line that the value of my function approaches, but it never touches that vertical line, is called a vertical asymptote. That's a new word for your glossary, so to speak. That's a new term that we haven't talked about yet. So a vertical line that your function approaches but never touches is called a vertical asymptote. And as we know, all vertical lines have this form, x equals a constant. So in this case, the constant's 1, because the line goes straight through, x is 1. Now a horizontal asymptote's a little bit different. It's a horizontal line that the graph approaches way out at the end. It's like, what value does this function approach when you're looking at the end behavior? So think about x being way out here at negative 600 million, oops, way out here at 600 million, and way out here at 600 million. The graph, no, it won't be. If you look at what's happening to the output as we get way out here, what's the value of your function getting really close to? It's getting smaller and smaller. It's approaching zero, right? It's approaching your x-axis. You can literally see the graph is getting really close to your x-axis, which means your output is zero. Your y value would be zero. So the horizontal asymptote is what does this function get close to? What value does this function get close to way out in the ends? It's really what's happening in the ends of the function. So 0 for y, yeah? Well, I didn't say it never touches. I said it never touches the vertical asymptote. Sometimes it will cross your horizontal. Sometimes. There are cases where you can cross the horizontal, but it can never cross. It's not parallel. It's actually getting closer and closer and closer. So it could intersect it. So it's not going to be parallel. Yeah. All right. There were like 3 questions asked at the same time. Nick?
So if it would say, like, say that shifted up like 3 units or something, so the horizontal then be.
Yes. And this is a good question because this is what we're going to do today. You know how to do transformations. So if we had an equation for this, which we don't right now because, you know, it would be kind of more complicated than what we need to look at today. But if you took this whole graph and shifted it up 3 units, then your horizontal asymptote would be the horizontal line y equals 3 instead of the x-axis, which is y equals 0. Because every value of x on your x-axis is 0, and it would just shift up to be every value of y would be 3. Yeah, so if we did a vertical transformation to this graph and put a +3 at the end of the equation, everything would shift up. Yep. Other questions? All right. So yes, if we shifted right or left, then the vertical asymptote would change. All right. So here's our formal definition of a rational function. Every time you see the word rational, hopefully you think of that first little word that's included in rational, ratio. And a ratio means you're dividing 2 things. And in this case, each individual numerator and denominator, if you just looked at the numerator separately, then it would be a polynomial. So in other words, if I take my magic pen out here and we just focused on the numerator, that would be a little baby quadratic expression, right? It's a 2nd degree trinomial, 3 terms, or a quadratic polynomial. And then if we came down here and we expanded, if I can make that circle a little bit bigger, this would be a 3rd degree because you've got 1, 2, 3 linear factors. You add 1 plus 1 plus 1, that would give you 3. And if you multiplied this all out, you'd get x to the 3rd as your first term. So this is a 3rd degree polynomial here. So if we divide these 2 things, then we're going to end up with a rational function. So the domain of a rational function, this is with polynomial functions, we didn't have any concerns because polynomial functions had all real numbers. We never had to be concerned about the domain. But now that we have a division problem, we have to worry about the big bad 0 being in the denominator. So when you're trying to find the domain for a rational function, the first thing you have to do is make sure you factor your denominator. And sort of here we have a little bit of a break because I've already factored it for you, right? So it's done. It's already done. So if we look at each factor in the denominator and set it equal to 0, then we can find the spots where our function is undefined, and that means we're going to have vertical asymptotes there. So look at each factor in the denominator, set it equal to 0, and find the excluded values of x from the domain. Yep. So our domain then, remember a domain is a set of is a set. So you never want to just put in the excluded values. You want to say it's a set of all x, except x can't be a 0, it can't be a 4, and it can't be a -2. So that's in set notation. If we did it in interval notation, it would go from -infinity to -2, union with -2 to 0, union with 0 to 4, and then finally 4 to positive infinity. It's a little bit of a pain to put it in interval notation. Sure. Yep. Yep. That was if you were doing a solution set, which is different because my math lab would never accept the domain in set builder notation. It only takes it here. But if you were solving an equation like a cubic equation, Nick, that had 3 answers, and you put it in the solution set, you would have to do -2, 0, 4. Okay? Yeah, Abby? Yeah. Can you hang on a little bit until Friday's class, because we're going to talk about this? Yeah, there is a difference, and I'll tell you right now what the difference is. This, if we were just looking at this, what would be? Let's try to make up an equation for this function. If we have a vertical asymptote at x equals 1, if x equals 1, and you solve this equation for 0, you would subtract 1 from both sides. So that would be a factor, right? Because when 1's here, 1 take away 1 is 0. So you're just working backwards from your answer to your factor. So we would know x minus 1 would have to be one of your factors in that domain, correct? You get that? Because 1 would make that denominator 0. So Abby's asking, where does this idea of the whole come in at 2? Well, this is where it comes in, and we'll explain it more on Friday. I don't want you to get hung up on it. You have a whole at an x value. So we just said x can't be 2 either. So if we go backwards and solve this for 0, we subtract 2 from both sides. So there must be an x minus 2 in the denominator. But guess what? There's also an x minus 2 in the numerator. So you'll get a whole with a rational function like here if the factor is common to the top and the bottom. It's common to the top and bottom. So you can reduce this, and what it really looks like is 1 over x take away 1, which is 1 over x shifted to the right 1 unit. Yeah.
Can you have a horizontal asymptote?
Yep, that's what we have right here. No, right here. This is your horizontal. Okay. It's right here, y equals 0. Okay. Other questions? Sure. Does that answer your question, Abby? Okay. Okay. All right. So we just found the domain for this rational function, which I'm not asking you to graph this right now, but if you were to graph this, right, you would have a vertical asymptote that goes through -2, like this, at -2. You'd have one, the y-axis, wow, whoa. The y-axis would be a vertical asymptote, and where would the other one be? At 4, right? All right. So see, it divides your domain up into 1, 2, 3, 4 sets of numbers, and that's right here. Okay. Yes. 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 Okay. So let's investigate the simplest rational function, just like the simplest quadratic function was x squared. We called that a parent function. We're going to call this a parent function. So I'm introducing you to a new parent function, 1 over x, a new parent function. Okay. So there's another name for this function. Does anybody know, other than calling it a rational function, what the other name might be? God, it doesn't have the name of a Greek god, no. It's an inverse. It's a multiplicative inverse. Yeah, but what's the name of a multiplicative inverse? It brings you
Function,
a what?
a sibling function, a daughter. Just
It begins with an R. Give me an R. Reciprocal function, right? It's the reciprocal function. Woohoo! All right. Because notice, whatever value you put in for x, your answer becomes 1 divided by x. So it's the reciprocal. So whatever you put in for your input, your output is the reciprocal. Okay, there's your x and y values for this function. So for this particular function, what would be the value that's excluded from the domain? X equals what? 0, right. So the excluded value is x equals 0, which means in set builder notation, my domain is the set of all x except for x can't be 0. And in interval notation, I can go from -infinity to 0 and be cool. But then at 0, I have that dotted line. Remember here, this is the y-axis at x equals 0. And then to the right of the y-axis, I'm cool again. I'm defined. So my domain is every single real number except for 0. That's the only one that the function's not defined at. So if I try to put a 0 in here, there's no number in the world that defines that division. Can this function, can 1 over x ever equal 0? Ramsey says no. No. Di says yes. There's only 2 choices, yeah. Let's see, how many people say no? Nobody raises. How many people say yes? We've got 1, 2, 3. We got 3 in that category. How many people say I don't know? Ah, a couple in there, I don't know. All right. All right, so let's take a look at this in general. How do you answer a question like this? Here's a fraction. When can a fraction equal 0? When the top is 0, when the numerator is 0. This can only equal 0 when the numerator is 0. Right? That's the only time. When the numerator is 0, that means your output would be 0, your y value would be 0. So what I'm asking here really is, can this function have an x-intercept? Because if it has an x-intercept, you know there's a value for x where your output is 0. Anytime your numerator is a constant number, there's no way that constant can be a 0. So there's no way this function could ever be 0. So in this particular case, this function has no x-intercepts. Because y can't be 0? Because your numerator will never be 0. Never be equal to 0. Now, if I had something up there like x plus 1 times x plus 2 times x minus 3, then there'd be a couple of different places where your numerator could equal 0. But whenever your numerator is a constant value, other than 0 itself, then that wouldn't be very exciting to look at anyway. Then you can't have any x-intercepts. All right, so let's take a look at graphing this function. This is going to be one of our parent functions we look at today, and we're going to look at a second parent function as well. So let's take a look at what happens to, we know that if we were graphing this function, that the y-axis is where we have our vertical asymptote. Our vertical asymptote, VA, is x equals 0. And we know we could never have an x value equal to 0 because it's undefined. So the question is, what's happening to my function as I approach x equals 0? And I've got 2 sides of this axis. I got all of the numbers to the right of 0, and I've got all of the x values to the left of 0. So we're going to chunk this out. We're going to look at the graph to the right of 0 and to the left of 0. So let's start by approaching 0 from the right. So this is the reciprocal function. So f of 1, what's the reciprocal of 1? 1. It's its own reciprocal. So at 1, I'm up here at 1. Here's 1, 1. Okay, I got a point. Good. Instead of putting decimals in, it's really easy for me to take reciprocals of fractions. So why don't I put each one of these decimals in its fraction form, because that's going to make life a lot easier for me to think about the reciprocal. Okay, so f of 1/2 equals 1 divided by 1/2, which is 2. So I'm going to go half the distance now to my y-axis, and I go up to 2. So is 1/2 2. All right, now I have f of a tenth. So that's 1 divided by 1/10, which becomes 1 times the reciprocal of 1/10, which is 10. Okay, shoot. I don't even know if I can get that close to the y-axis. All right, I'm way up here I'm really close. There I am. Oh, it's not on there. It's close. It's just the width of my pen here looks like I'm on the y-axis. So there I am, way up at 10. And now I'm at f of 1/100th. What would my answer be? 100. So I'm already like halfway up to the ceiling now, right, to plot my next point. And then f of 1/1000th, I'm at 1000. So I'm sitting up on the roof now, right? So this thing, as it approaches 0 from the right-hand side, is increasing without bound. So it's going to positive infinity, all right? So I can fill in this sentence right here. As the x values approach 0 from the right-hand side, that means in this particular case, all my x values are positive. The values of my function approach infinity. It's increasing without bound, going up to the roof and then to the stratosphere and out beyond forever, beyond to infinity, or whatever Toy Story said. All right. Shorthand notation for the above sentence. Mathematicians like putting things in symbols, so it's more universal. It's not based on a particular language. So to say we're approaching 0, we know this notation, x with the arrow, means x approaches 0. But this time we need to talk about from the right. We're coming into 0 from the right-hand side. So that's what this little plus sign right here means. We're coming into 0 from the right. So as x is coming in close to 0 from the right, the value of our function, the output, approaches infinity. It goes up to the sky. That's right. And so if you look at this for a second, just look at your function. So what are we putting in here? We're putting in here a positive number, right? We're to the right of 0. So our numerator is always going to be positive. 1 is always positive. And if we put a positive number in for our denominator, then that means when we divide two positive numbers, it's positive. So it's approaching positive infinity. So as Jasper was sort of thinking ahead, what happens now when we approach 0 from the left of 0? That means all your numbers that you put into your function, all your input, will be negative numbers. So f of -1 is -1. So over here, I'm at -1, -1, okay? And then f of -1/2 is -2, okay? And as I get closer and closer, I'm getting closer and closer to negative infinity. So this is going down. So it's just the opposite. When I put in opposite x values, my y values are opposite. That's a certain type of symmetry. We'll get to that in a second. So here's how we say that as the x values approach 0 from left, our y values approach negative infinity. This is the notation we use. And from the left is that little negative sign right there saying we're coming in from the left and the value of our function is approaching. It's going way down, down, down to negative infinity. It's decreasing without bound. And that's how we represent those two ideas. So in this case, we have a vertical asymptote at the excluded value x equals 0, which is our y-axis. Another name for that is the y-axis. So that's our vertical asymptote. And that's what I labeled right here, vertical asymptote at x equals 0. So to kind of finish this off, I have to think about what? The end behavior. What happens to the value of my function as my numbers go, my x values get bigger and bigger and bigger. So the bigger my x value is, what's its reciprocal? Yeah, you reverse it. So what is it? Smaller and smaller and smaller. What does it approach? 0. Because if you put 100 in, you get 1 over 100. If you put 1,000 in, you get 1 over 1,000. You put a zillion in, even though there's no such number, you get 1 over a zillion. That value, that decimal, is getting a lot more zeros after the decimal point, and you're getting closer and closer and closer to 0, which is your x-axis. So what's happening here is, as your numbers increase, this is getting closer and closer to the x-axis. Sorry, this is not allowing me to draw the way I want today. Okay, so your horizontal asymptote, that's the value your function approaches way out at its ends, is getting closer and closer to 0. So that's your horizontal asymptote. The horizontal asymptote is your x-axis, which is y is 0. So that's the x-axis. That's the end behavior. So how would we use our notation, our arrow notation, to describe that? So you say, okay, as x approaches positive infinity, the value of my function is getting really close to 0. As x approaches negative infinity, the value of my function is getting really close to 0. So it's the end behavior. Now the difference between rational functions and polynomials is polynomial end behavior was either rising or falling to positive and negative infinity. That was your only choices. You knew your graphs were going to you knew at either end it was going to rise or it was going to fall. The difference now with end behavior with these rational functions is that your end behavior, your value of your function, actually approaches a number for many of them. Okay, it's not infinity here anymore, negative infinity like you were used to. It's actually the value that the function approaches. And that's the big difference between your end behavior idea between rational functions and polynomials. Nick?
If you write it the other way around, as x approaches 0,
Yeah, that's what we have up here for the vertical asymptote. And for the vertical asymptotes, your behavior at the vertical asymptotes will always be the value of your function going to plus or minus infinity, always, because the vertical asymptotes is what drives this function crazy, right? It makes it like nuts because you're getting close to a value for which the function's not defined. So you'll see that negative and positive infinity with your vertical asymptotes. Okay. Yeah. Wait a minute, I can't hear you because people are talking what? Yes, sometimes they can be. In this particular case, we're going to have an even or an odd, and we'll see in a minute. Yes, but not all of them. Ramses?
When you're writing
Yep.
where you put the hole? If there was a hole in there.
The hole's going to come. This one won't have a hole, but the hole for that first function will be part of the domain, the excluded value for the domain.
Okay.
Okay? But this one has no hole because there's not a common, because if you look at this 1 over x, there's not a common factor top and bottom. In order for there to be a common factor, there'd have to be another x in the top somewhere. I mean, there's always 1 in the denominator, but that's not going to change this. 1 over 1x is still 1 over x. So, okay, so now we're ready to graph this function. Just knowing those couple of ideas, we know that we have a vertical asymptote at our y-axis, so you put a dotted line, and this is where your colored pencils will come in today when you're graphing this. In fact, feel free to take them out now. Your horizontal asymptote is the x-axis, so I'm going to make a dotted line there for my x-axis. I have no x-intercepts or y-intercepts to worry about in this particular case. I have more pencils up here. If you want them, I'll bring them to you. So I say, okay, as I get really close to the y-axis from the right-hand side, I get really close to that vertical asymptote, and my end behavior gets really close to my x-axis. So sorry for that little teeny bloop right here. Let me get that. Okay. So here we go. All right. I can't get much better because of this pen. So there we go. I don't have all these double lines here. So I guess I have to start from the beginning again. See, we're all anal. Math teachers are all anal. Right? So here we go. I'm not going to get any better until I I'm really messed up. All right. You know what it looks like. We just did it. What? Okay. And the other one goes like this. Gets closer and closer. It should be getting closer and closer to the y-axis. Yes. So you mean using a transformation? Is that? Yeah. Odd symmetry. Yep, you could automatically get the next one. Yep. So let me get a little different value, a picture here from the calculator. So actually, GeoGebra would give you a nicer picture, but see, just because my pen's messing up, this is all messing up. Okay. So you know what that looks like, right? Because we just drew it before without the pen messing up. All right. So what kind of symmetry does it have? Well, even symmetry says if you take opposite values of x and you put them into your function, then your output's exactly the same. Well, we know from this function that we have these points, 1, -1, and -1, -1. 1, 1, and -1, -1. So look, if you put in opposite x values, your y values aren't the same, they're opposite. So that means this is definitely doesn't have even symmetry about your y-axis, but in fact it does have odd symmetry, which says if I take my x value and I plug it into my function, and then I take the opposite of x and plug it into my function, then my two output values are opposite. And there you see the two output values are indeed opposite. So this has symmetry about your origin. So the distance from, in this case, 0 to 1 and 0 to -1 is the same. So how do you show that algebraically to confirm it? You say, okay, f of -x would look like this. I just put in a -x where I see x. And the opposite of 1 over x is that, and those two are indeed equal. So the negative what? That's the definition of odd symmetry. We've had that used that for many weeks, okay? That's the definition. All right, so let's take a look at the next function, and I want to try to get through this a little faster so we can indeed look at, oh, let me show you what GeoGebra looks like for 1 over x. It's right here. It will be a much nicer graph than the one I just tried to draw you with this pen not working very well. Okay, so again, you can see the behavior of the function. If you want, you can take your axes and, change the scales, and you can see how quickly the value of the function is getting close to the x-axis. It looks like it's right on top of it, doesn't it? And how quickly this gets really close to the y-axis. So if we just spread this out a little bit more, so you can kind of see some of the values. This is a nice picture of 1 over x. This is the reciprocal function. So let me put that in so you have a nice picture of 1 over x compared to what I just tried to draw for you. There we go. I'll just throw that into your notes. Okay, so here we go. That's a nicer graph than what I tried to draw for you. Okay. All right, so let's take a look at this function right here. It's another parent function, 1 over x squared. What value is excluded from the domain of this function? 0, same thing. Okay, so let's use our arrow notation to describe the behavior as we get close to 0 from both directions. So we want to fill in this. As x approaches 0 from the right-hand side, what does f of x approach? Stephen, do you mind getting that door for me? And as x approaches 0 from the left-hand side, what does f of x approach? So we want to think about the same thing. We want to think about putting small numbers in there. 1, if I put 1 in here, I get 1 over 1. If I put a half in here, I get 1 over 1/2 squared. So it's 1 divided by 1/4. So now it's 4, right? Instead of 2, it's getting, the denominator is getting smaller, which means your reciprocal is getting bigger much faster. So this is still going to grow towards positive infinity. It's just going to, your values of f of x are going to be bigger a lot sooner as you move in towards your 0. Now, the only difference between this function and our other function is now when we put in our negative values for x, what will be the sign of our denominator when we put negative values in and square it? Positive. So this is, from the left-hand side, it's going to approach positive infinity as well. Okay.
If that was an x cubed, would it be negative?
Yes, absolutely. Yep. So now use your arrow notation to describe the end behavior. Well, now remember your end behavior is x goes towards positive infinity and as x goes towards negative infinity. So f of x is still going to approach 0 in both of these cases, which is your x-axis. And so what's the equation of your horizontal asymptote? Our horizontal asymptote is every horizontal line is y equals a constant. In this case, it's 0 because the value of my function is approaching the x-axis. Does this have any x-intercepts? Absolutely not, because our numerator is 0. This function can never equal 0, so no x-intercepts. And y-intercepts is when x equals 0. Well, guess what? X equals 0 is excluded from our function, so it has no y-intercepts. So the answer is nope, nope, and nope. All right, so let's sketch this graph. So this graph, the end behavior is getting really close to 0, and it's getting really close to the y-axis. And whoops, went the wrong way. I'm above the x-axis because everything's positive. So here we go. Okay, as close as, I'm having a hard time with this pen. You get the idea. Huh? It would if it was just x squared, but you can't have a 0, so you can't have a parabola here. X can't be 0.
They just parallel.
They're exactly this. It has even symmetry. Because if you put 1 into this function, out comes 1. If you put in its opposite, out comes the same value. Because when you put in, so to show even symmetry, you go like this. And 1 over the opposite of x squared is x squared. So that shows you even symmetry, that you have even symmetry. Yep. So for every point on this side, Ramses, there's an equivalent point on that side. Yep. Okay, so that does it. Now, let's just take a look at your first class activity. One of the things I probably should have written in here is we have the parent function, but what would be really nice is if you could just state what the transformation is from the parent function to this function. So if we look at this first function, f of x equals 1 over x minus 5. Now, we only had two parent functions to look at, 1 over x and 1 over x squared. So what would be the parent function to that function? 1 over x, all right? G of x is 1 over x. Let's call that our parent function. And so what's being affected here? The output or the input in this function? Output would look like this. The input, your x is having all your x values is having 5 subtracted from it. So this is a horizontal shift to the left. Five units. So this goes back to Nick's question earlier. So if you think about your one reciprocal function, all you're going to do, did I say to the left? Nobody even said anything. What is it? To the right. So all that's going to happen is your entire reciprocal function is just going to move to the right 5 spaces. So in this case, you will have a y-intercept. Okay, you will definitely have a y-intercept here. That function, the y value can equal 0. Get it? If the y value equals 0, that's an x-intercept. So what's a y-intercept? No? What's the y-intercept always have? X equals 0. If you put a 0 in for x, what's the value for y? Negative 1/5. So it has a y-intercept, but no x-intercept because the top is 1. So you work through these. You got plenty of time. You got 20 minutes. And ask me if you have any questions. I'll be glad to help you.